Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Groundwater Hydrology and Management. This is NPTEL course, week 6, lecture 2. In the previous weeks, we looked at the importance of groundwater and most importantly, the key parameters for groundwater. In this week, we are looking at why groundwater level would fluctuate, and in particular, we are looking at groundwater recharge and discharge. In the last class, we looked at the key functions or processes that influence groundwater levels. Let's move on and look at groundwater recharge in this particular lecture. So groundwater recharge can happen through multiple processes. However, it is important to distinguish between groundwater recharge and discharge. What we saw in the previous class is that one in the hydrological cycle, that one process can lead to recharge and also discharge in the same process. The flow of water from the high aquifers into the rivers and lakes is an example. Yes, it is discharging, but on the way it is recharging. So for that, we are going to look at what are the common methods in which these are assessed. We looked at the processes, now look at how they are assessed. It could be different for recharge and discharge, but there are some processes or some methods that can capture both. For example, the water balance method. Here, you put in parameters for your water balance, and then you can estimate where the recharge is happening and discharge is happening, or both are happening simultaneously. For which there is a lot of monitoring needed and or understanding of your properties of the soil, the material, and water, rainfall, hydroclimate, etc. Water balance method can also be done like back of the envelope calculation people do. You have a surface runoff coefficient and then you have rainfall. We say that, okay, whatever is not runoff is going into the ground. And into the ground means it is groundwater recharge. So there are some simplified models, but we will look into very specific models and methods that are used for recharge and discharge in the coming lectures. The other method is monitoring method. There's a lot of sensors that can capture the parameters to assess the fluctuations in the water level. For example, monitors or meters and sensors that can help in the water balance method, which we explained using this hydrological cycle. You have multiple components and you can put values for each component based on the recordings of these meters and sensors. Then you have groundwater recharge monitoring, specifically for groundwater recharge monitoring, which is done by wells and the well level recorder or meters you use to record the well levels. For seepage, there is a different method. For example, you have water coming, you can put a meter inside and then calculate the groundwater recharge or fluctuation or discharge using a water meter. On the other hand, the water can go and get into the ocean and rivers and lakes, which is called seepage. And that seepage can be estimated using a seepage flux meter, which is a meter placed on the banks of the rivers and oceans and seas to monitor how much water is coming out. It may be easier for estimates in the oceans because there is a density difference in the water. However, it could be more difficult in the rivers and freshwater bodies. So monitoring can help in establishing the water balance components or specifically only the groundwater wells or the seepage. The third point is estimates. There are lots and lots of estimates that are made. And these estimates, as I said, are based on the back of the envelope calculations, very simplified calculations, which are coming because of a prior understanding of the system. Let's take this example, right? Your change in groundwater is nothing but del G, change in groundwater level, is equal to precipitation minus or rainfall minus runoff. As I tell, the parameter variable differs. You can put rainfall as R or P, etc., but it's all same. How you define it is very important. So in this equation, I'm defining it as del G, which is your difference in groundwater level, which is the fluctuation, is nothing but your rainfall, the water coming onto my land, minus the runoff. So if I extract the runoff, if I subtract the runoff volume, whatever volume remains is going into the ground. Remember, there's no ET, there's no evapotranspiration, there's no other losses, because I'm taking a very specific case study where I don't have all these. Let's take a barren land, for example. Okay, in that barren land, there's no plants, there's no evaporation also happening. It's just going in because there's no sunlight, for example. The rainfall only happens in the night. And in the night, there is runoff happening, and most of the water will go down the remaining water and reach as a groundwater. These are the estimates that you can put with the back of the envelope. And even the R, which is your rainfall, which you need data, or every month you have a statistical model to predict the data. But Q can be, most probably, they do estimates. If you know, for example, it is a cement road. If you know, for example, it is a forest, you know that 80% of the water will run off. The remaining 20% will go in. So those kind of percentages are estimates based on previous field work from different locations. Then you have models, like this model you have here, which is the SWOT model. Very complex hydrological models, which if you give all the parameters ranging from the top water meter models, water balance data, etc., you feed it into these models, and the models give you the output of groundwater recharge or discharge based on your calculations and based on your estimates of these parameters. So for example, you give all these parameters in the model will spit out a groundwater recharge value and a groundwater discharge value. It also is based on the climate, the land use, which is your trees, plants, etc. growing, and your slope of the land, how the land is tilted and stuff. Let's look at some of these estimates, especially the recharge estimates. So now we're going to shift gears in just looking the recharge volumes for India, and also only India. Okay. The first is our own Central Groundwater Board, where it says annual replenishable groundwater resources are 433 billion cubic meters. The net annual groundwater availability is 398 billion cubic meters. And your annual groundwater draft for irrigation, domestic and industrial uses 245 billion cubic meters. Okay, so this 433 is based on annual data of how much water can be used to recharge. Okay, the net groundwater availability is the water that is remaining to be used, because not all 433 can be consumed. Part of it is going to be held in the soil and the rocks and other materials. It is not going to be taken out, which is here. It is approximately 35 billion cubic meters. It's a big amount, but it's still, think about pan India. This data is for pan India. Okay, so I didn't say that. This is data for whole of India, CGWB estimate. And then you have your annual groundwater draft for irrigation, domestic, and industrial use. Basically, these are three different uses. And if you understand what is the draft or pumping or use for irrigation, because of the crop type, crop area, you know how much water is required for irrigation. Domestic, you know how many people are there through population census. And from the census data, you can estimate what is the number of households, and each household how much water they get for estimating domestic water use. Then you have your industrial use. Industrial use is the trickiest here because it is closed. Let's take a bottling company, for example, where they make fruit juices, drinks, soda, etc. It is a big industry which takes a lot of water. We don't know how much water they use. Okay, they have pay per use system and or lease system. They'll say, okay, 100 years I will pay this much money, or 10 years, 30 years. And the pumps efficiency only they know. Okay, you cannot estimate it just by power supply and all, because they can keep fine tuning the efficiency of these pumps. So what happens is the industrial use is still a big estimate, where irrigation is also kind of monitored and measured, because you know satellites can take pictures of crop types, and domestic use you can take it from census, which is a survey based data. So all this data is available. Industrial is kind of really tight, but you can manage. You can estimate as CGWB has done, and it is saying 245 billion cubic meters. This is kind of an outdated number. Now it is 265 billion cubic meters. So what is the stage of groundwater development? Now you know the draft. You know the recharge, which is around 433 billion cubic meters recharging, out of which 398 can only be used. And out of the 398, only 245 was used, which is 62%. So 62% is nothing but the percentage of 245 in the 433, almost around 50 plus, right? So it's 62 percentage, which means that it's still safe. India is safe in groundwater use as per this CGWB estimate. It may or may not be the same by other estimates. Let's look at some other estimates. This is the estimate done by your team in Banja et al. Paper 2019, where they use explicitly lot of wells, groundwater well data, and they measure the recharge happening and also the precipitation happening per year. Okay, so millimeters is a thickness, not a volume, but a thickness of recharge and thickness of rainfall happening in a year. And note that they only do it for India, and because of the data they have, and there are multiple transboundary rivers also here, like your Indus, Ganges, and Brahmaputra. Could be multiple transboundary. Ganges goes from Tibet, China, Nepal, and India. Indus can be Pakistan and India part. So there are differences. Brahmaputra, the Bangladesh, etc. So here only the India part is spoken. And what you could see is the number of wells help in estimating the recharge for sure. And there is differences in groundwater recharge. The differences is led by the groundwater parameters, which we saw earlier in the class of the importance, which is basically your aquifer type, the soil material, the rock material present in that basin, which allows the groundwater to flow, the ease of groundwater to flow and recharge. Not only that, the area should have a good rainfall. You might have the best groundwater aquifer, but if you don't have rainfall, water doesn't go in. So water is important, and after water, the water from rainfall, the rainfall should go into the aquifer. So the availability and readiness of the aquifer to recharge is also important. And in that aspect, you could see that the recharge ranges from 143 to 264. Barak and other basins are 94 to 960, whereas the Brahmaputra is anywhere 94 to 960. The Barak is 77 to 802. So mostly your alluvial aquifers, which are given in this first couple of things, most of these basins I'm saying, where the alluvial aquifers are more. you could see a very healthy groundwater recharge, okay, compared to the other regions. Actually, all of them are basins. So all of them have a river and stuff. So you will see some part of alluvial in it. But what is the major discussion in this slide is that you have multiple wells that can give you accurate data for estimating recharge. And the recharge is not the same across India. This is the driving factor. Okay, it could be 960 in the Brahmaputra, whereas it is only 131 in the Pennar basin in the south. And this is where I say it is also based on the rainfall, which is 2,300 in the Brahmaputra compared to 779, almost arid, semi-arid condition in the south of India, Pennar. And you also have the aquifer type, the geology, which is allowing the recharge or not. So recharge is a good combination of your rainfall availability, your physical processes, the aquifer properties that allow the recharge, and the availability of water inside the aquifer. If the water is already there, recharge won't happen, right? So this study beautifully quantifies across India through wells, the recharge rates, and also compares them with the rainfall rate. And most importantly, they establish the range. So the range could, why is there a range difference? For example, you have the Brahmaputra, let's say this is the Brahmaputra, the Ganges looks somewhere like this. So you have 143 to 264. Why is there a range difference? Because the rainfall also varies, even though they give only one rainfall here. Okay, let me erase some of it. Yeah. So then you have multiple wells in different locations. The rainfall is not the same, but still, let's say on average, this is the rainfall. But there is very, very important change in the groundwater recharge because of the location, aquifer type, and the slope and the rainfall also differs. Along the Ganges, it is not the same. Okay. Okay, so this study is very important to quantify the differences one can expect because of the placement of the basin in a particular aquifer system or a geology type, and also the rainfall. All of this is driven by your well record. So different estimates are there. This is the other confusing part. This may not agree with the CGWB's estimate. The differences can occur because of the well type. Maybe they're using more deep wells to establish the aquifer recharge conditions. And also the region. In the previous slide, you just saw 245, 433 as a recharge annual. But where is it placed? Where is that 433 billion cubic meters happening? We don't know. It is a combination, but which regions have more and which regions have less, we don't know. This gives a good picture of where in data where it happens more. Okay, so as I said, more recharge is happening in the Brahmaputra compared to the other regions, and then the Pennar in the south have very, very less recharge. Let's come back to the book that we're using for the class, which is the Hydrology Principles and Analysis, designed by Professor Raghunath. And what you see here is water is taken as rainfall, and then an estimate. See, here's the estimate at 1/3. So this estimate is given. It is not, or it need not be a calculated, monitored, report sensibly acquired data. It is a 1/3 based on literature review. So they say the rainfall is 370 million hectare meters. It's a volume. Okay, hectare meter is a volume. See how the units change. So it's not readily comparable. The previous slide, it was millimeters per year. In the previous slide, it was billion cubic meters per year. So in the CGWB estimate, it was a volume. In the next slide, the Banja et al. Paper, it is a thickness. Here, it is a volume. Okay. So evaporation at 1/3, 123. Runoff from rainfall in rivers is 167. As I said, they'll just estimate how much runoff. Seepage into soil by balance. Okay, so how much is seepage happening? You just subtract 1, which is your rainfall, and then 123 and 167. So if you know one quantity in your water balance, you can estimate the other components by a simple addition or subtraction. Okay, so here they've added 2 and 3 and subtracted, excuse me, to get at 80. So this is the groundwater recharge. See how the language is. Seepage is used here, which is basically your recharge into the subsoil, into the soil. Water observed in topsoil, contribution to soil moisture. This is also an estimate. Okay, he has put 43, and 43 is from the 80. Okay, so what is the recharge for the deeper aquifers? So recharge into groundwater from rainfall, the net recharge which is going into the aquifers after the water is absorbed or in the soil moisture is only 37. So seepage is here is just the infiltration. Water infiltrates, part of the water stays in the soil, which is 43. The remaining goes down as recharge, which is 37. So 43 plus 37 is 80. Okay. Then your annual groundwater recharge from rainfall and seepage from other canals and approximate. They've put it very clearly, blatantly, which is good. If you don't have the data, read some books and papers and put a number and say it is an estimate. Do not say it is actual value. So these are actual, rainfall is actual. You cannot say that. You can just say approximate. Then groundwater that can economically extract from the present drilling technology at 60%. So 60% is again a number. They put that on 7 and then take 27. Present utilization of groundwater at 50%. In the previous CGWB slide, it was saying 62%. Here they're using 50%. Maybe when they did the book in 2006, it was a CGWB estimate. Okay, ours was 2010 past it. So there is some difference in the percentage. So let's say 50% of 8, or 50% reduction is 13.5. So available groundwater for future exploitation, which is the remaining 50%. Okay, 50% is utilized, 50% is remaining. So that is 13.5. So you see here how water balance equation is set up in the mind, or and then they've written it down, identified which are the key parameters and thrown out the negligible parameters like ET, capture, water capture in the canopy, those kind of things through rainfall, etc. They lift it out. We don't know, we don't want to. And then they put estimates for each and every parameter, 1/3, 50%, 60%, and then arrive at recharge. So this is another way of estimating groundwater recharge. So this is 37. It could be also be done with the equation I gave you, which is del G is equals to just rainfall minus Q. So if I assume there's no evaporation, I say rainfall is happening, 370 minus runoff, 167 is the net recharge in my very simplistic case. It is approximate. Please read in between the lines. Is it an actual data? If it's an actual data, they'll give you the data source. Otherwise, it is approximate, and there are differences. Okay, they have identified only parameters that they want to be sure of. The others, they give it very blatantly. It is an approximate. So driving home here is there are multiple methods for estimation of groundwater recharge. It can be based on multiple physical or data intensive or modeling perspectives. Let's look at some of them. The very, very important, as per the recent review by Sajil Kumar in 2021, and also as defended by the Freeze and Cherry's groundwater book, which has identified the most important groundwater recharge estimation methods. So now estimates is important. Like you saw that different estimates are there. Not one method is important. There are multiple methods depending on the data, depending on the cost, depending on the time for the research project. Let's look at some physical methods. This needs a lot of physical data. Okay, the soil water balance method by Thornthwaite is an example where you construct a hydrological water balance only for the soil, because you don't care about the evaporation, you don't care about how much is left in the rainfall, etc. You only care about how much water comes in, and out of that, what is the reallocation to plants, animals, etc., and how much water goes in. So this is a soil water balance method which is developed by Thornthwaite, nothing else but a water balance which is focused on the soil water. So you have the groundwater surface. You have the water table in dashed lines, and then you have multiple instruments that can collect data at different depths. For understanding groundwater recharge, understand that the first set of tensiometers here will only look at infiltration, slow infiltration of water. And then you have a rainfall gauge to look at how much rainfall is happening. So you have the input to the system, you have the first seepage infiltration into the system, and then you start slowly monitoring your groundwater wells. The soil electrical resistance is a device that is used to measure the soil moisture. Once the soil moisture is full, 100%, then water goes down. If soil moisture is not 100%, water still stays in the soil, slowly recharging. The soil moisture, not the groundwater. We are here looking at groundwater recharge, not soil moisture recharge. Then you have observation wells, which is your wells with a meter in it, and all piezometers, which are deep aquifer wells. So these two are just wells, but the difference is the depth. You can see here how deep it is. It is a broken y-axis. So it is not going in tens and hundreds. It goes different units, okay, depth in feet. Then you have zero flux plane ZFP based on Darcy. Remember, Darcy's is a saturated column, and how water flows through this plane is determined by Darcy's flow. So Darcy's flow, if it is kept only in this soil profile, gives you the groundwater recharge. After that, you can use the Darcy's flow here to look at groundwater flow. Remember your class notes that we use Darcy to estimate groundwater flow. But Darcy's principle can also be used as a recharge. All you're doing is shifting from the confined aquifer and unconfined aquifer into the zone where water is coming into the soil. It is recharging and then comes out, which is recharge. Again, recharge is also a flow. It happens from top to bottom. It goes down in the soil profile. So there is a groundwater level fluctuation method, which is one of the most important methods used worldwide, including USGS, including CGWB. Always people use this groundwater level fluctuation method, for which there is a need of groundwater data from these wells. And then you have the groundwater balance method, which is another soil water balance type of water balance, but only kept for the groundwater. We've already seen these water balance equations in the previous class. All of these need extensive data. That is the driving point. Then you have tracer techniques. Here comes the kind of an invasive way of testing groundwater, because you are now getting into contact with the water. Here you're just measuring the water, that's it. Here you are putting something in the water to measure it. Okay, please understand, here it is need of not data alone, but need of chemicals. You're going to put a chloride. You're going to put a chloride to see how the chloride signal travels, or tracers like environmentally friendly tracers, inks. You can put an ink to see how groundwater recharge happens. But then there are tritium method and stable isotope method, which are water signature methods, which are based on the chemical property of the water. Okay, so tracers not only include the inks and biological or chemical traces that you add in the water. It can be also done by analyzing the water chemicals components or the isotopes that are present. In fact, the isotopes are very useful for understanding the age of the water. Then finally, we have the numerical methods, which are based on pure modeling. There are softwares which actually ask you for a lot of data, and then it is a data heavy, but there are models which can also estimate for you. You just have to tell, this is the type of soil, this is the rainfall, this is the crop I'm growing. It automatically tells you the groundwater recharge. Okay, and within the groundwater model, you have multiple dimensions. There can be a 1D, which is just looking at one dimensional movement of water. There can be a 3D where kx alone is not only there, but also you have kz, ky, and kx. So 3 dimensions how groundwater moves, and the net groundwater flow is going to be modeled. Hydrus is a good model for 1D, whereas ModFlow is a very good model for 3D. And then you have inverse modeling, which is also based on a lot of data. So here we have seen that establishing these connections on how recharge happens, like the physical establishments, you can have different estimates based on different methods. There is no one method that is being promoted across the world. It depends on your region. It depends on the data you have, the time, and the resources. For example, for numerical methods, it is very important to have a very sophisticated computer. Otherwise, the model will crash. For tracers, you need a good environmental tracer or a clearance from the government to test these tracers. Most importantly, the stable isotopes and tritium would need a radioactive lab. It is not easy to do all these. The physical methods are more easier. You have to put data, collecting, monitoring sensors, collect the data, come back, do the calculations by hand or by computer, and then you estimate. So there is give and take in each method, and what method is suitable for you, you could use it for the long run. Okay, so we've looked at the different methods. We will look into one or two methods for this class, and then we'll jump into the discharge methods. With this, I will see you in the next class. Thank you.